Okay, so I am going to be making several presentations today. So a bit after lunch, I believe I'm going to be talking about user-level security challenges on the blockchain, as well as proof of stake. But in the morning, what I wanted to start off with is basically just a simple, kind of very low-level hands-on introduction to kind of the nitty-gritty of how launching and running smart contracts on top of Ethereum works. So in general, if you are going to be doing any serious Ethereum development, there's probably a few major tools that you're going to want to be familiar with. So this is the Geth Lite client. So the Geth Lite client does have an interface, but I'm a command line sort of guy, and so I'm using the command line interface. And so this is the Geth Lite client. So this is not a full implementation that downloads all the blocks and all the transactions. This basically downloads all of the block headers, and if you want to grab any particular piece of information, then basically the client actually asks the network for a Merkle branch, and it verifies all of the hashes, and it actually verifies that, basically it asks some other node to tell you what some piece of information is, uses the Merkle tree to verify that that information actually is the thing that got committed to in the block headers, and then it returns it to you. Right? So if, for example, I want to do something like get ETH.balance of ETH.accounts 12, and then, now the reason why it took about a second there is because when I make this call, it actually makes a request out to the network, and it basically says, dear network, I would like to know what the balance of this account is. Please give me the response, and please give me the Merkle branch that proves it. And so some node replies, and I get a response. Now you might notice that I get a few quadrillion units, actually a few quintillion units of something here. Now this does not mean that I'm rich enough to have 990 quintillion units of Ether. What this is, in Ethereum, just like in Bitcoin we have Satoshis, in Ethereum the smallest indivisible unit of Ether is something called a Wei, named after Wei Dai. And one Ether is 10 to the power of 18 Wei. So if we want to convert this from Wei, then there we go. See, this account only has 9.98 Ether. So and you can do a lot of different things from this client, from the command line interface, but this is only one tool of several. The other major tool that you'll probably want to be looking at is Etherscan. So Etherscan is a block explorer, so similar to what blockchain.info does for Bitcoin. And it basically just tells you a lot of information about the blockchain, lets you check the status of transactions. It has a lot of really convenient tools. So for example, we can go into the charts, and we can go into the transaction history, and we can see that Ethereum has been doing very well lately. So that's, it's been about 5 transactions a second on average for the last few days. Then there's also another one that's called EtherChain, and that has some interesting data on it as well. So this is just one particular chart, and this basically just shows that right now the blockchain is around 70 blocks in Ethereum are about 75% full. So there's several different websites that you might want to kind of look at, and they all give you information about the Ethereum blockchain in different formats. Etherscan is also nice because it has this broadcast raw transaction text box, where if you create a transaction using another tool, then you can just push it here and you broadcast it. Now the reason why this is convenient is because there might be situations where the Geth Lite client works imperfectly if you have a crappy internet connection, and so you might want to have a backup, and this is one of the backups. There's also another thing to look at, which is myetherwallet.com, and this just is another site that just has a lot of different convenience tools for sending transactions, sending tokens, participating in ENS, just doing a whole bunch of different things. And I'll wait for that to load. So those are online tools. Another kind of tool that people often like is the Aetherium Tester. So this is if you are completely offline and you just want to do local testing of stuff to do with smart contracts, then you can do by the way, can people see what I'm typing here? Okay. Yes, Python 3.6. There. So one important thing about Ethereum is that in the previous presentation, they introduced Solidity, but there are actually multiple different high-level languages that all compile down into EVM code. And the one that I'm going to be using more of today is something called Viper. And it's in some ways similar to Solidity, except it has a kind of more Python-like syntax, and it has a bunch of other interesting features. But basically you can, if you want to, you could use either one of the two. Solidity is probably more kind of mainstream and well supported now, but Viper has in disclosure, it is the language that I came up with, but it has a growing community as well. So here, who here does not understand what this highlighted program does? Okay. Do you understand? So this is a function definition. And it declares a function called foo, because foo is like a standard name that computer scientists like calling functions. And the output is a number, and the function returns the number 3, right? So this, and over here, what I'm doing is I'm basically trying to call that function. Now, what's actually happening here in the back end, as you might notice, is this is a kind of tester module that basically it actually initializes an entire kind of local private chain. So when you do this C equals tester.chain thing, it actually creates a local private Ethereum chain that only exists inside of this Python console. Then when I do this line of code, it actually creates a transaction and publishes it into the private chain. And this transaction creates a new contract, right? And then after this, what I'm doing here is I'm kind of calling a function of the contract. But in Ethereum, calling a function of a contract actually is sending a transaction that has data that's formatted in a particular way. And we can actually check this. Here, let me, for our convenience, let's encode hex this. There. So you might notice that actually we'll just do import RLP as well. RLP.hexencode. C.lastTX. So when I did, so the last operation that I did is I called foo of this contract, and that actually was a transaction that got published to our mini private chain, and this is the kind of binary serialization of that transaction. Now, you might ask, well, why such a big transaction? The basic answer is that transactions have several different kind of. I can do this, and this should might make it slightly more simpler. But transactions have, as you saw in the last presentation, a few different components. So this thing is like a nonce. It basically is a number where every time you send a new transaction, it has to go up by 1, and that prevents replay attacks. This is the gas price. Now, because it's my own private chain, I'm making a gas price of 0. In kind of real life, you want the gas price to be much higher. This is the amount of gas, and this is just like a couple of bytes. If you really want to, you can convert it into an integer. Actually, let's just do that. There, see, the gas is 3141592 apparently. This is the in binary form the address that I'm of the contract that I'm calling. So if we want to, we can, there. So currently Ethereum does have a checksum scheme, and it's this kind of it's this backwards compatible overlay thing where basically the address gets hex encoded, and then depending on the hash of the address, random letters in the checksum encoding end up getting kind of capitalized or not capitalized. And this basically just reduces the risk that if you mistype something, then like most of the time it'll catch the error. Then over here, this represents the fact, I mean, this is obviously the binary encoding of, anyone want to guess which number is the binary encoded as the empty string? Hint, it's not 4. 0, okay, yes, this is 0. And then over here, this is the transaction data. So every transaction has a data field. Now, if your transaction is just sending Ether, then the data field is useless, right? The only reason why you might want to fill it is maybe because you want to send a message along with the transaction that says, you know, this is paying for like invoice number 135452 or whatever. So, but if your transaction is going to a contract, then the code of the contract has the ability to read this transaction data. Over here, the transaction data is just 4 bytes. And the hex-encoded version of the 4 bytes is this. Now you might ask, well, why the 4 bytes? And the answer is that in Ethereum, there is this set of scheme that's called the ABI, that we call the application binary interface. And the purpose of the ABI is basically that it converts function calls into into bytes. So the first 4 bytes of an ABI encoding are an ID that represents the function. So in this case, this is an ID that represents the function foo, and if you want to know how we get the ID, that's actually pretty easy. There it is, right? It's basically just like, it's basically the SHA-3 of the function signature. That's now if you want to do more things, then you can do more things. And I'll show more things. So for example, how about right now we're going to try making a somewhat more complex contract. And this more complex contract is just going to be a simple splitter. So every time you put money in, it sends half to one address and it sends half to another address. So because this is a function that you send money to, we have to explicitly declare it payable. And we're going to call it split. And we'll say A1 address and A2 address. And we'll say send MSG A1 MSG.value over 2. Send A2 MSG dot value over 2. And then we'll say x2 equals c.con code. And for the language, we'll say Viper, and we'll say x2.split, and we'll use some of tester's built-in addresses, and for value, we'll just say value equals something, and there, and that just, now you might notice this particular piece of code doesn't return anything, so it looks like it did nothing, but in the backend, it actually did split the Ether in half. So this is all kind of on a local private network. Now what happens if we want to do something on a public network? So how about, what we're going to do is we're going to take this exact same piece of code and we're going to run through an entire process of publishing this on the actual Ethereum main chain. So just for kind of educational purposes, I am going to use fairly low-level tools to go through all of this so we can see every single step. But as an actual developer, there are, when you actually start developing applications, there are much higher level tools that you can use. And if you're a user, then you should be using user interfaces that are written by developers. So not everyone has to go through all of this torture. But anyway, so what we're going to do is we are going to, first of all, I saved a file, and this is a file that I saved. This is my wallet file, and yes, you can feel free to take there. And now the wallet file is encrypted, right? So actually, so what we're going to do is actually, hold on, let me look at some Actually, we'll start off by going through, going from here. There, so we can, there. So you can see how these accounts all, like this particular account has some Ether in it. And so what we are going to do is, first of all, we are going to say from Ethereum import the ABI. And from the ABI, we are going to, basically we are going to create an object in Python that does a contract translator, and the contract translator is going to just say, hold on. So what we're going to do is from Viper import compiler, and CT equals ABI dot contract translator, and the contract translator will be of compiler dot make full signature of the code that we have over here. And then, so we'll start off with that, but first what we're going to do is we're going to go with C equals compiler dot compile for the code. And this is the code in Viper compiled into EVM code. So now what we're going to do is we are just going to utils.encode hex this. And if we want to publish this code, then first of all, we are going to do a personal, we're going to have to unlock this particular account there. And then we will do a send transaction. And we'll say from accounts number 12. Then what we're going to also specify is for data, we're going to specify this. And for gas, we are going to specify 300,000. And for gas price, just to get this in quickly, we're going to specify, let's say, roughly 30 billion. Now we're going to try and publish this, and there we go. Now we get to see an Ethereum transaction actually going onto the mainnet, right? So we'll just wait for this to load. And there we go, it already got confirmed, right? So let's go through some of the details of this transaction. Now, because I don't have too many minutes left, I promise this is the second, if everything works, this will be the second last transaction I send here, but we can go through some of the details, right? So first of all, every transaction has to specify something called a gas limit. And you can think of the gas limit as just being the maximum number of computational steps that this transaction is allowed to take, right? In reality, it's not really computational steps because, as we saw earlier, different operations in Ethereum have different gas costs. But you can think of it as kind of the quantity of computational resources used up by this transaction. Then this is the actual amount that was used up. So we asked for 300,000, used about 120,000. This is a transaction that created this new contract. So if a transaction does not specify that it's going to an existing address, then it interprets the transaction data as code and it tries to create a new contract. Then the gas price is the transaction fee that we pay per unit gas. So in this case, it's 30 gwei, which is about 30 billionths of an ether per gas. And the total fee ended up being this. It ended up being $1. Creating contracts in Ethereum is more expensive than doing other types of transactions, so you're encouraged not to create new contracts too much. And this is the input data, and we see that it already had one confirmation because with a high transaction fee, it can be fairly quick. So now what we're going to do is we are going to say that the address is, so this is the new contract address that we created, right? And hopefully we'll be able to see, if we see get code, there we go, it's in there already, right? So now what we are going to do is we are going to try to encode and then split, and let's say we are going to use these two accounts, and we're going to try and split some money between these two accounts. So, and we're going to utils.encode hex this. And then, now this is a more complex ABI declaration, right? So this is still the exact same kind of application binary interface we know and love, except you might notice that this thing over here now is up to 68 bytes, right? So the first 4 bytes represent the function, so in this case split. The next 32 bytes are the first argument, then the next 32 bytes are the second argument. So while you're sticking with kind of fairly simple types, the ABI is actually very simple to encode and very simple to understand. Now, what we are going to do is we are going to say eth.sends transaction from also eth.accounts 12. This time we're going to say to the contract, and data is going to be 0x this. Gas will be, we'll make it 120,000, and gas price will also, we'll also make it about 30 billion. And we're going to try sending this. Now, by the way, there's nothing special about me using the number 301112222333. The main reason I do this is just as a trick to prevent myself, to make sure that I'm not accidentally setting it 10 times too high or too low. Because if you set it 10 times too low, the transaction doesn't get included. If you send it 10 times too high, then you've wasted $9, which can apparently buy some pretty good falafels in Israel. So, yeah. Let's see the transactions, and we can see that this is a transaction which is still pending. Now, the transaction inclusion is a fairly kind of stochastic process because, look, first of all, you have to wait for blocks to get created, and then, oop, I think I just forgot something. So what did I just forget? I forgot that. There. This is the, so this transaction is probably going to do nothing interesting, but this transaction is hopefully going to do something more. So now basically all we really have to do is just like wait for this thing to get included, and realistically, it might take a small amount of time, and it might also take a large amount of time. Let's see, nonce 18. There we go. This transaction has successfully been included and will be updated shortly. And there we go. See, so this transaction, because the transaction did not come with any ether, it ended up dividing the 0 ether by 2, and it basically sends 0 ether to one address and 0 ether to another address. But with this transaction, I actually remembered to send some ether, and you can see it sent half to one address and half to the other address, which is exactly the thing that, hold on, print code there, which is exactly the thing that the code says that it does, right? So there you go, your first experience to a very low-level Ethereum programming. First experience to very low-level